Now we're going to take a look at the continuous case. So we proved that cyclic monotonicity is a necessary and sufficient condition in the general case. But is there anything that continuous case would give us? Because in the continuous case, it's kind of hard to understand how would we form those, graphs, and how are we going to find those maximal paths to compute the payments. So let's address that. So in the continuous case, we are going to assume that the set of types is a subset, probably a convex subset, or like a nice subset of the vector space of dimension D. But we are not going to use any additional assumptions on the set of possible outcomes. So this could be a discrete set, it could be a continuous set, doesn't really matter. The additional assumptions that we are going to need is that the value function, which in the discrete case was just a table, in the continuous case, this value function needs to be, we are going to assume that it's a differentiable with respect to the first argument. So specifically, what does it mean if the second argument maybe is just a set? Well, then it would just be a collection of differentiable functions, which would be indexed by all those possible outcomes from the set of outcomes chi. But every function in there would be differentiable with respect to the first argument, with respect to the first argument t. So we have this cyclic monotonicity condition, and let's just write it out again, just for reference. So we have v of ti plus 1, t x of ti minus v of ti x of ti, and the I goes from 1 to n, and this holds for any finite cycle t1 to tn, where tn plus 1 cycles back to t1. Now let's take a look. Let's just visualize it a little bit, and let's take a closer look what is going to go. So let's imagine this is our cycle, and let's consider like the sequence of those cycles with more and more dense number of points. So in the limit, this would approach like a closed curve in this dimension, in this space of dimension D. So this is just a curve. And let's take a look at those 2 points that are really, really close, that are basically infinitely close to each other. So for those 2 points, what do we have? We have that v of ti plus 1. Well, let's say that ti plus 1 is just basically this ti plus some dt, just a very, very small, tiny vector pointing from ti to ti plus 1. And then we are going to have that this ti plus 1 x of ti minus v of ti and x of ti. We can use the first order approximation for this v of ti plus 1, assuming, and we have this assumption that v is a differentiable function. So what would be this first order assumption? It's going to say, okay, this is ti plus dt x of ti, and this is going to be minus v of ti and x of ti. And we are going to expand it to the first order. So this is going to be taking this v at ti, and plus the gradient of the function v with respect to the first argument t at ti and x of ti. So this is going to be a vector of dimension d, and we are going to take a scalar product with the dt, and we also had minus v of ti and x of ti. And yeah, those things are canceling. So we end up with with this first order approximation, then this difference, this weight of the step. So this is what used to be the weight in our direct acyclic graph. Here is this ti and x of ti times this this very small increment vector dt. And note that in this limiting case, this very, very little cycle here, like very, very little, very closely spaced points, the weight of going into the forward direction would be equal to the weight of going into the negative direction. So this is for like very, very small increments that this would hold approximately, but sure, the smaller the increments, the better this thing holds. And now we are going to consider the limit. So let's take a limit with number of points on this curve, on this closed curve going basically to infinity, of all those cycles of vi ti's plus 1 x of ti's minus v of ti and x of ti's from 1 to n. So now we are considering this more densely and densely spaced points on that curve, and we end up with an integral. So this is going to be an integral over this closed curve gamma, and we are going to use our approximation. So this is going to be the gradient with respect to t. And just to make the notation a little bit more precise, I'm going to use a different variable of integration. So this is s and x of s times ts. So this is the curve integral along this curve, closed curve. Now, the cyclic monotonicity condition tells us that every finite cycle had the weight less or equals than 0, so we can conclude that in the limit this also holds. So this integral is less or equals than 0. Well, on the other hand, consider reversing the direction. So let's assume that we were integrating in this direction, and because I already mentioned that when those increments get smaller and smaller, the weight of going from I to I plus 1 and back, they approach each other. The only thing that is going to be different is the direction, right? So this is basically what I'm trying to say here is that by reversing this curve, we are going to get an integral. So let's call this maybe integral j equals to j of gamma. And let's take a look at the j of going into the opposite direction over the same gamma. So this integral is going to be over this over the same curve in the opposite direction. Now it's going to be the same here, x of s ds. And again, by the same arguments, this integral should also be less than 0 by cyclic monotonicity condition. But also we know that by reversing the direction of the integration, we have the condition that, well, j of gamma is equals to minus j of gamma bar. So the integrating in the other direction. And well, we have that this thing is less than equals than 0. and this thing is also less than equals than 0, we end up that the reasonable conclusion here is that integral does not really depend on the direction, and it's equal to 0. So equal to j of integrating in the opposite direction, and it is equal to 0. So what we've got here is that cyclic monotonicity is equivalent to saying that the integral over a closed curve of this function, the gradient with respect to t of value function s and x of s ds over any curve is equal to 0. Well, from here we will get that the integral between 2 points does not depend on the details of the curve of integration, but just on the start and end point. So let's see that. But consider 2 points, t1 and t2. And what we want to prove now is that the integral between t1 and t2 over any path does not really depend on the path. So this is going to say that well, the integral from t1 on some curve t1 that visits t1 and starts at t1 and ends at t2, maybe like this. And the other one maybe like this. And this goes this way, and this goes this way. Equals to the integral of a green one, t1 and t2, some other gamma prime. How can we show this? Well, this is basically shown by saying that, okay, so if we reverse this this green curve to this direction and form a cycle using green and using blue and reversed green, we are going to end up having the integral that is going to be closed curve integral going from t1 to t2, and then this is going to be using blue, and then going back from t2 to t1 using like green, but reversed green. This integral is going to be equal to 0. And well, again, because the reversing the direction just flips the sign of the integral, we end up concluding that those two integrals are actually equal. And we can write it as j of gamma equals to j of gamma prime. So this means that we are actually integrating over the gradient of a potential function, because this is the property of the potentials, that the integral with respect to this curve integral over these gradients, they do not depend on the details of the paths of the integration. They just depend on the starting and the ending points. Okay. So we can also write it as u of t2 minus u of t1 is the integral over the curve gamma that goes from t1 to t2 of this of this gradient t in v of s x of s ds along any curve. So any curve would work here. Now let's use this to show that the integral between 2 points is going to be that maximal path. So remember that we've defined the payment as the maximal path, the path of the maximal weight between 2 points. So what I'm going to prove now is I'm going to show that the integral here is the largest path, and therefore it could be used to define the payment. How can we prove that? Well, let's consider the following cycle. First, we travel from t1 to t2 using the integral from t1 to t2, and then we just jump straight back using just a single step. So when we are going to prove that for any 2 points, we get that the integral, like a continuous integral around any point, like using any curve, is greater or equal than the direct step here in this direction. So let's try to see that. Well, we have the cyclic monotonicity condition. So the cyclic monotonicity condition tells us that the integral, let me write it as a j from of the gamma that goes from t1 t2 plus, and now the jump back. So we have v, and we are going from t2 to t1, so this is going to be t1 and x of t2 minus v of t2 and x of t2. And we also have that if we consider this reverse, this other path, the integral that goes from back. Also, I forgot to say that this sum is going to be less than equals than 0 by cyclic monotonicity condition. Now we know that the integral of gamma t1 to t2 plus the integral using some gamma prime going from t2 to t1, this is equal to 0, right? So now we have that we have that v of t1 and x of t2 minus v of t2 and x of t2 is less than equals than minus j of gamma that goes from t1 to t2. So this is by just taking this and sending it here. And now using the second one, we are going to replace, to substitute it here. So we are going to end up with v t1 and x of t2 minus v of t2 and x of t2 is going to be less or equals than our red integral over this sum path gamma traveling from t2 to t1. And well, and this thing on the left-hand side is the definition of the weight of going from T2 to T1. So what we have here is that the the weight of a direct jump from two to one is less or equals than the integral over any path going to from T2 and T1. And this could be extended basically by induction, that any discrete path would consist of those jumps, right? And then so this is like going from T1 to T2, and then we have that we can construct those integrals like a curve that goes from here to here to here to here to here and to here. And the curve, the integral over the curve is going to be larger than the sum of those discrete jumps, because for every jump we have that this segment of the curve, the integral over that segment of the curve is larger, or not less, at least not less or equal. And then we also have that the integral doesn't really depend on the exact details of the path. So we can consider any arbitrary path that goes here. And therefore we conclude that the integral over any path going from T1 to T2 or T2 to T1 doesn't really matter. So let's keep the notation as it is. T1, T2 to T1. This integral does not depend on the details of the path, and at the same time it's better, or at least not worse than any sequence of jumps. So this is therefore this is actually the supremum, and this allows us to use it to define the payment. So the payment of t is going to be v with respect for we are basically we're using the same definition from the discrete case, but here this is going to be an integral over any curve gamma going from T1 from some reference point T0 to T with a gradient with respect to the first argument. So let me be a little bit more careful here. T of S, X of S, and ds. So we've got this definition. We've got this definition of how to compute the payments in the continuous case. So in the continuous case, this is going to be the value in subtracting the element, and well, this is by definition is going to be the utility. This is why the notation utility of the player, because the utility is what player gets, like what value he gets, minus minus the payment, right? So that's why we have that notation for utility. So this is a pretty general result, and let's just maybe have a little bit of visualization here. So we have let's do a two-dimensional visualization. So we have some decision rule. It could be like a discrete case. Like let's for example take a look at the two-dimensional case T2 and T1. So there are two dimensions, and it could be that there are a set of outcomes maybe looking something like this. So here we get the outcome x1, here we get the outcome x2, and here we are going to get outcome x3, right? So in order for this to work, we need the following. We need to make sure that our decision rule X works like this. We should be able to take any starting point and any ending point and draw any curve around here. And the computation of that integral should not depend on the path. In particular, it's pretty easy to understand what it means in a special case. So the special case, particularly interesting special case, is linear special. So in the linear special case, what do we have? We have that v of t and x is going to be just a scalar product of t, scalar product x. So in this case, we assume that the t and x, they have the same dimensions. Still, x could be a discrete set of possible outcomes, but they should have the same dimension. So this scalar product would make sense. So let me write maybe like this scalar product here. Well, now we can see that we have this. Let me just write it again. We have that the payment function is going to be v of t and x of t. Well, now this is, we can simplify because we have our linear assumption. So this is going to be t scalar product x of t minus integral from some t0 to t. And we need to take the gradient of v of t with respect to the first argument, which basically leaves us with just x of s ds. So in this case, this visualization makes even more sense. But additionally, we are going to show that in the linear case, there is a necessary condition. The necessary condition is that u of t is a convex function, x of s is a subgradient of that function. We have v of t and x of t minus p of t greater or equals than v of t and x of b minus p of b. So this is our truthfulness condition. So this is why we are talking about necessary condition now. Put the linear case here. This is the u of t on this side is greater or equals than, in here we are going to plug v of t as a linear. So it's going to be t scalar product with x of b minus, and then there we have this p of b, and we can expand the p of b here as v of b x of b minus u of b. So this is going to be minus v of b and x of b plus u of b. Okay, so what we get here is that u of t is greater or equals than some u of b plus scalar product of x of b, t minus b for all t and b in our set of possible types. So what does it mean? This means that we have a function u of t, and okay, let's try it. This is the function u of t, and at every point of that function, some b. So let's make this point b. We have a linear function that is equal, that is equal to our u of t at this point, but everywhere else it lies below, right? So this is like something like this, and the tangent of this plane is x of b. Well, this exactly is the definition. So first of all, we know that our u of t is formed as this envelope of those linear functions. So everywhere we have this happening, and therefore we can conclude that u of t is convex, and then x of b are those tangents of those supporting hyperplane, supporting linear functions. And this is the definition of the subgradient. So x of t belongs to a subgradient of u of t. Well, this specific notations belongs to a subgradient is just because for convex functions but not differentiable functions, it could be that there are this corner points, and in the corner points there could be many possible supporting planes here. So those could be number 1 and number 2 and number 3 and all, and all family of those, and like this. And in fact we have so here we have that the x of t at this point t should belong to a subgradient, meaning that it should be one of those planes. And now this visualization for this linear case makes even more sense, because now we can see that let's think about like a projection to a two-dimensional plane. So our x of t should be a projection of a gradient of a convex function. So there is a convex function. Our projection would look something like this. It's not possible for this function to look something like this. So for example, here we are going to get x1, the outcome x1. Here we're going to have our outcome x0, and here we are going to have outcome x2. These zones should be convex zones themselves, because if we imagine the convex function that is it's basically this convex function should be made out of those supporting hyperplanes. And if we are thinking about the set of discrete choices, those planes, they would form like a polyhedral, something like a polyhedra. In the projection of it would be something like this. It would look like a structure with those complex domain. I mean convex domains, where each domain would be a projection, where this subgradient would have just a single value. But those points, this edge points, those are going to be the points where two of them meet together, and there we would have this kind of situation.